All right, so you get to choose problems to do. I'll do all four. I'm going to go and do them in the order that I would have chosen if I were doing these problems, though. First, I would definitely tackle the integral of ln of x using integration by parts, since that's sort of quintessential, and I know it takes just a single use of integration by parts. So for that one, we are looking at setting our u equal to the ln of x, which means our du is equal to 1 over x dx. Our dv is equal to dx, and our v is x. So when we go ahead and use the integration by parts formula, we have x ln of x minus, and I'll go ahead and be slow here, x times that 1 over x dx, which we know is just 1, so let's go ahead and write dx. And then we're at our final answer, x ln of x minus x plus c. Now I'm reconsidering what I did with those signs on the last one, but it's fine. Doesn't matter. Cute. We're done. So I'm going to move on. The next one I would probably choose to do. I know I only need a single integration by parts step in that bottom right, so I might head there. In fact, let's just go ahead and do that. 3x plus 2 times sine of x over 2 dx. Really nice, just a linear function times a trig function. Both are really easy to work with. We know we should set our u equal to 3x plus 2. du is equal to 3 dx. My dv is that sine of x over 2. And that means my v is cosine, and it would have to be a negative cosine of x over 2. And then I would have to deal with that u sub, add that 2 back in front, because we would have divided through by a negative one, by that 1/2. So again, applying the formula, we have negative 2, I like to throw that in the front, parentheses on that 3x plus 2, because that entirety is our u, times cosine of x over 2. And then we need to do minus, but we do have a positive, we do have a negative there, so plus 6 cosine x over 2 dx. So one more step and we're done. We already have that first term, but we need to take the antiderivative on that second term that we have. It looks like we have 6 cosines, so this will become a sine of x over 2. We'll end up multiplying by that 2 again, just like we did in our first, when we found our v. So this will be a 12 plus c. Perfection. All right, so we got our first two. So those are the two I probably would have chosen as a student. If you're really a big fan of tabular, you might choose bottom left. She's pretty slick, right? This is the one, x cubed x 5x dx, x cubed 3x squared, 6x, 6, and then if you want, you got your 0. Our e to the 5x, we'll take antiderivatives in this, or in this direction, which means we'll just keep dividing by that 5. You can see me not sure I can, I got it. 1 over 625 e to the 5x. All right, and then we know we're just multiplying down this, plus minus plus minus, as we distribute all the negatives that would have happened in that minus of our v du. So final answer here will be, let's put the 1/5 out in front. Oh, with a negative. Whoop. Negative 1/5. Oh, that's positive. No, it is a negative. No, the negative is not on the 1/5. This is just crappy notation on my part. I'm like, I couldn't even tell the negative was attached to that second diagonal, but it's fine. All right, we have 1/5 x cubed e to the 5x minus 3 over 25 x squared e to the 5x plus 6 over 125 x cubed e to the 5x, x cubed, lies, x, and then minus 6 over 625 e to the 5x plus c. Definitely some patterns here you can leverage to make sure you don't make any like silly mistakes like I almost did. All right. And now the last one, the one I absolutely don't think is the choice on this, is to grab the one where we have to do that doubling back to our original integral, and we see it appear in our integration by parts. So e to the 2x cosine of x dx. So I'll just e to the 2x, maybe I should make a line, I have enough space. I've already forgotten what it was. E to the 2x cosine of x dx. All right, so our goal here is to do integration by parts until we get back to the same integral that we started with. Your choice entirely, which one of these you make your u and your dv. It does not matter, you just need to stay consistent. As I said in the previous video, I love whole numbers, so my preference would be to make my u my e to the 2x because now I don't have a fraction. And then our dv is the cosine of x, and my v is sine of x. All right, so we now have that this is equal to e to the 2x sine of x minus, we can pull the 2 out in front, maybe not, that doesn't matter. I'm going to go ahead and leave the 2 in the integrand here, and I'll show you why. Okay, so we're going to do this again because we still have another problem child here, right? We still have the problem of having an exponential function times a trig function. So I'm going to make sure to still use my u as the exponential. I'm going to go ahead and bring the 2 with it just for funsies. This will help me make sure that I'm distributing the 2 to every term that needs it. And then we have 4 e to the 2x for our du. My dv is sine of x, which means my v will be negative cosine of x. Okay, so here's what the magic happens. We're going to rewrite this one more time, bring everything down. E to the 2x sine of x minus, we have, we're going to have times the negative, so it'll become plus 2 e to the 2x cosine of x. And then we need to subtract off, but again, we have a negative. Oh God, I just lost my brain. We have this minus, but then we're negative. Okay, I think we have 3 negatives. We have the negative that's in front of all this nonsense. We have the negative from the integration by parts formula, and we have the negative from our v. So we will actually stay negative on this one. This is when parentheses and maybe moving a bit slower would save you. Maybe a little bit of that tabular method to double check your pluses and minuses would be nice here. But we end up with 4 e to the 2x cosine of x dx. All right, so let's go ahead. Whoop, e to the 2x cosine of x dx. I'm bringing this down so we can see what we're equal to. So this is the goal, is that we have an integral here that completely matches the integral right over on the right-hand side. And so we can just say, well, that's awesome. Let's add 4 of this integral to both sides because these are like terms. And a lot of books and folks out there online use I to rewrite this because, I don't know, it's funsies. So we have 5 of my e to the 2x cosine of x dx is equal to e to the 2x sine of x plus 2 e to the 2x cosine of x. And now I no longer have an integration symbol on the right-hand side, right? I don't have an indefinite integral over there. So the fact that I have an indefinite integral on the left-hand side means that I need a plus c, so I'm going to add in my plus c at this stage. And then I have one more step to get back to what the heck my original problem was that I'm trying to answer. I need to divide everything on the right-hand side by 5. And I can include the c within these parentheses or not. Truly doesn't matter because 1/5 of some unknown constant is the same thing as some other unknown constant. So anyways, that's our final answer for the last one. No reason to choose that one unless you just want to show off that you can do that out. And again, a little bit of tabular to like double check on your signs and your multipliers might be pretty nice here. Like if you thought about the pieces here, we had e to the 2x, 2e to the 2x, 4e to the 2x, and on the other side we had cosine of x, sine of x, and negative cosine of x. We had a positive, we had a negative, and then Oh, then we have to, this is the one we have to actually write the other way. See, it's still such a pain in the ass. I don't know, not my jam, not my jam, but that last piece is that I'm coming back for. So anyways, a longer video, but showing you all 3 different integration by parts, and hopefully you can decide which one you think is easiest. Like I said, no matter what, I probably would have done ln of x. A lot of students have trouble with that, so they might have done, I think the most popular ones when I did this last year were to tackle the bottom right, that 3x plus 2 times sine of x over 2, and to tackle the x cubed x to the 5x using tabular.